Yeah, this video is all about equivalent circuit of induction motor. The induction motor is similar to transformer. Only exception is the secondary winding. In transformer, we have primary winding and secondary winding. That is, secondary winding either will be connected to the load or it will be left free. But here in this induction motor, the secondary winding, which is termed as rotor. In induction motor, we have only two parts. One is stator and rotor. The stator is similar to the primary winding in transformer. And the rotor is similar to secondary winding in the transformer. The secondary winding, that is rotor, will be short circuited. That's the only difference. As we noticed in the transformer, it is easier if we can combine these two circuits, that primary winding and the secondary winding, in a single circuit, then the difficulties will be solved. This is the equivalent circuit. Let me explain this part one by one. The left side of this rotor, the center part is the rotor, and the left side of this indicates the stator windings. The circuit of stator is defined in the left side, and the circuit of rotor is defined in the right side. And for sure, this cannot be combined in a single circuit, because in between there is an air gap, so the electric circuit cannot be combined. Suppose we can explain this with transformer. The magnetic circuits can be included in between. So let me take you to the three-phase induction motor explanation here. As we all know, this figure shows the construction of three-phase induction motor or single-phase induction motor. When a voltage is applied to the coil, current flows in the winding and flux is established, just like a transformer. The air gap in the rotor is much larger. You should remember this. The air gap is much larger, and so the reluctance is higher. The reluctance is higher, so inductance will be lesser, and so there will be higher current will be flowing through the induction motor. For example, it will be 40% of the rated current will be flowing in the induction motor when there is blocked rotor. Blocked rotor in the sense rotor is not started right now, but there will be 40% of current flowing inside the circuit. But in transformer, during blocked rotor or during no current in the secondary, there will be only 5 to 6% of current flowing in the primary side. But here 40% of current will be flowing in the stator side. I am just comparing both the transformer and the three-phase induction motor only because then we will understand, because we have already seen the transformer circuits. So in developing the equivalent circuit of induction motor, we can recall the equivalent circuit of transformer. See, in the primary winding we have Rx, and we have another X which is related to magnetic reactance. See, there are three elements. One element is Rs, that is stator winding resistance. Xs, which is leakage resistance, leakage reactance, or it can be taken as a stator reactance. And Xm is another one, which is magnetizing reactance. These three components are there in the primary side or the stator side. Looking at the stator circuit, we can easily draw this. See, we are supplying an input which can be taken as V1, voltage supplied to the stator side. There are three components. One is Rs, second one is Xs, third one is the Xm. Let me take the current flowing through the stator side is I1. So I1. So let me write the equation like this. V1 is the input, so input is equal to E1. E1 is the drop at Xm. So E1 plus I1 into this circuit. If you know electric circuit analysis, then this equation will be understood by you. V1 is input equal to the terminal voltage E1 plus I1 into Rs plus Jxs. I1 is series current flowing through these two. So it is I1 equal to Rf plus Jxs. Okay, this is your figure number 1. So this EMF is the induced EMF in the stator, and this EMF is going to produce the rotating magnetic field in the stator itself. Due to this EMF cutting the rotor, we produce that produces the EMF in the secondary, which is taken as E2. Okay, here we are just linking this E1 with E2. Since E1 is the reason for E2, we are taking E1 itself for the secondary. But in secondary, we cannot mention it as Xs, Rs. Instead, we take it as R and XR. It is rotor resistance and rotor reactance. And the current flowing through the rotor is taken as I2. Okay, the current flowing through stator is I1. Current flowing through the rotor is taken as I2. Okay, now we are trying to combine these two into one. When the rotor starts rotating, then this XR will not be taken as XR. Instead, it will be taken as S into XR. See, when this rotor starts rotating, the frequency changes, so we have to include the slip inside everything. The slip will change XR and the slip will change E also, but the slip will not change resistance, because resistance in any circuit is constant. It won't change according to the speed of the motor or according to the slip or according to anything. Okay, only the E is changed and XR is changed, reactance and the E is changed. So E1 should be replaced by S into E1, XR should be replaced by S into XR. So these two changes should be incorporated. So for rotor alone, we incorporate SE1 and SXR. So the current circuit will be changed like this. The input is S into E1 for rotor, and I2 current the same. RR will not change, so it will be RR. XR is changed as S into XR. Here S denotes slip of the motor. Okay. Then after drawing this circuit, if I write the equation, then it becomes S into E1 equal to I2 into RR plus SXR. We don't have any magnetizing component in the rotor side, so there is no magnetizing component. So what they are doing mathematically, they divide the equation by S, so it becomes E1 plus I2 into R2 by S plus J into XR. This is taken into account, and directly we are coming here to the next circuit. This is how we deal it. We'll directly go to the explanation that we have given, share it to students. See, in the stator side, it is V1 as input, R1 is the resistance of stator, X1 is reactance of stator, and R0 and X0 are the magnetizing component. That means no load components. Okay, these two are no load components. When there is no load connected at the rotor, when the rotor is 0, it is not rotating, it is R0 and X0. So it is connected in parallel to the rotor. And in the rotor we have only R2 and X2. After it starts running, X2 becomes XS2, S into X2, and E2 becomes S into E2. This is what is taken. And E2 by E1, the two EMF is that. One is E2, which is rotor EMF, and E1 is stator EMF. If E2 by E1 can be taken as K, that is the constant. Okay. Substituting all these values, you will get the equation as this. See, what is I2? I2 is nothing but E by Z. Generally, I is equal to V by Z. So here voltage is taken as EMF. So I2R equal to E2R divided by Z2R. So instead of Z2R, we can substitute R2 plus S into X2. Since the equation for Z is R plus JX, we have taken the magnitude. So it is root of R2 square plus S into X2 square. Substituting everything, you will get I2R equal to S into E2 divided by root of S square and root of R2 square by S square plus S into X2 the whole square divided by S square. Cancelling everything, at last you will get like this. See, R2 plus R2 into 1 minus S by S. This is all derivation, just a simple mathematical derivation. You go through all these things. Dividing the equation by S, we are getting R2 plus R2 into 1 minus S by S. Here R2 is the resistance of rotor and S is the slip of the motor. Okay, here only two parts. R2 by S has two parts. One is the rotor resistance, which represents the copper loss, and R2 into 1 minus S by S, which represents the load resistance. So two components you should remember. One is the loss, another one is the load resistance. So I am going to divide the X2 component into two. Sorry, R2 component into two. One the copper loss component, another one is the load component. So equation and the diagram becomes like this. When we want to combine, when we want to take rotor side into stator side, represent everything in dash. All the rotor components should be represented with dash. So E2 is represented with dash, I2 is represented with dash, X2, R2, everything represented with dash. So E2 becomes E2 dash, I2R becomes I2 dash, I2R dash, X2 becomes X2 dash, and R2 becomes R2 dash. So the equation, see, I am taking everything of the rotor to the left side, so introducing dash with all the components and combine it. That's it. If I want to take the stator side to the rotor side, so I have to introduce all the stator components with dash. That's it. So R1 becomes here, R1 becomes R1 dash. Everything should be taken in the stator side to rotor. Stator side should have dash. That's it. These are the two different types of mentioning the equivalent circuit. Two things we have to remember here. One, only the E and X changes when the rotor rotates. There will be no change in the resistance. Okay, and you should introduce a slip when there is a rotating part, because slip is only representing the change in frequency and change in speed. The change in speed and change in frequency is represented only by the slip. So taking that into account, we are changing the equivalent circuit like this. Okay, this looks like a transformer. When we take rotor side to stator, rotor circuit component should be introduced with dash. When we take stator side to rotor, the stator component should be taken with dash. That's it. This is what is all about equivalent circuit of the induction motor. Thank you.